Hello, everybody. How are we doing tonight?
Yeah, good. Thank you, Professor. How are you?
I am well, thank you. All right, so as we get started tonight, the plan is for tonight, we're going to finish up our lecture number 4 was the one-way slab design. And then most of what we'll do tonight, we'll see how far we get, is on what's called a T-beam. So T-beam design and analysis. Before we do that though, before we jump into the slide, I had a few notes for you. I graded your first homework over the weekend, and I annotated or I commented on your homeworks as to where issues were. So hopefully you've all had a chance to check that out and see what the issues might have been. But I did notice a few common things that I wanted to clarify for everybody. First thing that I saw more than a few times, so I wanted to make sure everybody is clear about this. In a few instances, a few of you calculated your area of steel by trying to use basically the area of a circle, pi r squared. And I just want to make sure everybody understands that you cannot do that for rebar. Rebar is, it doesn't exactly follow the equation pi r squared because the diameter of the rebar is a nominal diameter. That's not the actual diameter of the rebar. And it has ribs and little deformations on it. So anyways, for a number of reasons, although it may get you close, using pi r squared or pi over 4 or any kind of an attempt to calculate the area of steel using the diameter will not work. And you can't do that. So you have tables. There's a table in your book, there's a table in the code, and there's a table in the first lecture that I gave. You have resources to look up the bar area in the tables. Please understand that is the only approved way to do it. You cannot calculate your bar area based on pi r squared or pi over 4 or anything like that. Second item that I noticed is quite a few students did not calculate the beam width, the minimum beam width. And if they attempted to calculate the minimum beam width, they attempted to calculate with a row minimum or something like that. That is not what we're looking for at all. What we're looking for is physically, is the beam wide enough to fit the rebar that you want to fit with the proper spacing? And please look in your textbook. In your textbook on page 86 to 88 is the procedure to calculate the minimum beam width. And also lecture 3 that I gave, if you download the PowerPoint, it was located on PowerPoint slides 182 to 193 is the procedure to calculate the minimum beam width. Okay, so does anybody have any questions about rebar area or minimum beam width? Yep, Simon, that's totally fine. You can use table A5, which gives you the area steel based on the number of bars. That does yield a slightly different number. Slightly. So the other table, let me get to my appendix here. Sorry, bear with me. I'm going through the appendix. Okay, so table A.2 has the cross-sectional area for every bar size from 3 to 18. And then what Simon said is table A5. Oh, the minimum beam width. Yes, you can use that. But table A4 has the area of each bar size from number 3 to 18 times the number of bars from 2 to 22. What I was going to note is that the numbers in A4 are just slightly different than if you took the number from A2 and multiplied times the number of bars. And that's because the numbers in the table A.2 are rounded up just slightly. So either one is acceptable. Use table A2, multiply times the number of bars, or use table A4 and look it up to the number of bars. And they should be really, really close. Okay, any other questions about that? Rebar area, minimum beam width. Alrighty. So let's jump back into our presentation on one-way slab design. Again, I'll ask one more time, any questions on one-way slab design that you had from last time before we plow forward? Okay. So we're going to start with our first example for a one-way slab design. Okay, so for this example, we want to design the negative moment flexural design. And for this problem, assume to use number 5s. So I'm basically choosing the bar for you. We're going to use number 5s. The area of a number 5 from those tables I just said is 0.31 inches squared. The diameter of a number 5 is 5/8 of an inch, or 0.625 inches. So seems like I'm missing a diagram. A second here. Oh, that's why. Okay.
Professor, what PowerPoint is this? I don't.
Yeah, I think I didn't start early enough. Yeah, no, I don't think my memory's going to poo.
No, Professor, we were doing the negative moment part. So we finished the positive part.
Thank you. Okay, so we did this.
Yes.
Okay. Okay, well, let's start from here again, and we'll just go through this rather quickly. But if I was lost, I'm sure you guys, some folks are going to be lost as well. So let's do this. What we started last time, this is our design situation. The design slab is 12 feet wide from inside a beam to inside a beam. We had a dead load of 100 pounds per square foot. That did not include the self weight. We have a live load of 100 pounds per square foot. We calculated the minimum slab thickness based on the expression of ln over 28. We chose a 5.5 inch thick slab. So then we decided to design a 12-inch wide by 5.5 inch thick slab. We found our dead load to be 169 pounds per square foot. Live load's 100. We factored it. We got 363. So for the positive moment, we have a discontinuous end integral with the support. As you can see here, this is my end bay support. So the moment that we're designing for is WL over 14, which was 3.73 kip feet, or 44.8 kip inch. That moment occurs, positive moment occurs in the middle here between the two supports. And then our negative moment for a member built integrally with the supporting spandrel beam is WL squared over 24 at the exterior face of the first interior support. More than 2 spans, it's WL squared over 10. And this one is the one that controls. So WL squared over 10 is 363 times 12 squared over 10 is 5.23 kip feet, or 62.7 kip inches. Okay, so let me, wish I had another diagram here. Okay, so what we are doing is we have a positive moment right here of 44.8, and then we looked at the negative moment here and the negative moment here. And of these two, this is the one that controls, and that's the one that we just calculated as 62.7 kip inches. So that's where we're at. We're basically just using the ACI equations to figure out what our worst moment equations are. So 62.7 kip inch is our maximum negative moment. Positive moment region. Okay, so for the positive moment, I'm going to do my flexural design. I'm going to use number 5s. My D is going to be the 5.5 inch slab that I assumed, minus 3/4 inch cover, minus half of my bar diameter, gives me the 4.44 inches. So then my RN, my reinforcement index, is MU over phi BD squared. Some of these things are going to start looking really familiar because I keep using the same equations over and over. Again, in the positive moment, it was 44.8 over phi, my assumed width of 12, my D of 4.44, gives me 210 PSI. From the text table A12, that gives me a rho of 0037, which is greater than 0033. So I meet my requirement for rho minimum, and it is less than 0.0136. So I meet my maximum steel requirement, which gives me an epsilon sub t greater than 0.005. Okay, so right here in this very condensed form, I did my maximum steel and my minimum steel checks right here. So the steel that I need is rho times B times D, which is 0.197 inches squared. Required spacing for a number 5 rebar. Okay, I would write this down in your notes. This is a very handy way to figure out what the spacing of the rebar needs to be for slabs. This does not apply to beams. Beams are a totally different animal. You shove all the steel in the bottom of the beam in the width that you have. But a slab has virtually unlimited width. So you're not going to specify 487 number 5s. You don't do that. What you specify is a number 5 bar at S spacing. Okay, let me say it one more time. For a beam, you specify the size of the bar and how many bars you have. 6 number 10s, 8 number 9s, whatever. For a one-way slab, you do not do that. For a one-way slab, what you say are number 5s at 18 inches on center, number 5s at 12 inches on center, whatever the design calls for. Okay? Any questions about this? Okay, so the required spacing for a number 5 bar follows this equation. It's the area of a bar divided by your required area times 12 inches per foot. So I put in my area of a number 5 is 0.31. My required area, I calculated, where did I calculate that? Right there. 0.197 goes there times 12 inch per foot, and I get 18.88 inches on center. That's my, by design, this is my required spacing. I cannot space them any further apart. The bigger that spacing is, the less steel you're providing. So this is a minimum, or I'm sorry, a maximum. This is a maximum spacing. But we also have,
Professor,
yes,
what do you mean by on center?
on center means that that is the distance from the center of a number 5 to the center of the next number 5.
Ah, okay.
So between each bar then. So it'll be one bar, 18.8, and then another bar.
Yes, yes, but on center means that it's not the space between the bars, it's the distance from the center to the center of the bar.
So we measure from the center of the bar to the other center of the bar.
Yes.
Okay.
And that's what
radius, space, and radius again.
I'm sorry?
It's like the radius of the first bar, and then the spacing, and then another radius of the second bar, right? Center to
Yes.
center. Okay.
Yes, yes. Or the way that they actually build these is if you say I want a number 5 at 18 inches on center, then what they do is they'll mark their formwork with a crayon or pencil, whatever, and they'll just measure out 18 inches and put a mark. Measure out 18 inches, put another mark. Every 18 inches, they put a mark. Wherever there's a mark, that's where they put a rebar. Okay?
Okay, thank you.
Do you only, I'm sorry, do you only calculate this S on slab designs? We never do this on a beam design?
That is correct.
Okay. Thank
That
you.
is absolutely correct. Because a beam, that there's a fundamental difference between a beam and a slab. A beam has a finite width to it, and that width is usually less than 3 feet. It's somewhere between 1 and 2 feet usually. So the spacing is kind of meaningless in a beam, but a slab is the width of the whole building. So you have to specify your rebar as a spacing on a slab because it doesn't make a whole lot of sense to tell them the total number of number 5. You're not going to tell them I need 780 number 5s. What you're going to tell them is I need a number 5 at 18 inches on center, and somebody else figures out how many of them they need to buy. Does that make sense?
Yeah, it does. Thank you.
Okay. So by design, I cannot put my bars any further apart than 18.88 inches on center. However, ACI section 24433 has some prescribed maximum spacing. Remember, we covered this before, and it is the lesser of 5 times the thickness of the slab, which would be 5 times 5.5 inches is 27.5 inches, or 18 inches. So you can look at it as 1, 2, 3. Whichever is the least of 1, 2, or 3, that's your design maximum. So in this case, 18 inches is your design maximum.
Professor, how did you get 18? Exactly 18?
From this section,
Okay.
24433. It just says 18. There's
Okay.
no calc to it.
So it's a standard.
Yes.
Okay.
Yep. Okay, so of the 3, the 18 controls. So we're going to specify, and again, remember what we're doing is our positive moment. So for our positive reinforcement, we're going to say number 5s at 18 inches on center. And when they build this thing, they can put them closer together if things get scrunched up or whatever, but they cannot space them any further than your design of 18 inches on center. Okay, so now what we're going to do is we're going to reverse this, because if you notice, we did our minimum steel check, our maximum steel check, but we have not done our strength comparison, our phi min greater than mu check. We haven't done that yet in all this work. So in order to do that, I need to know what is the actual area of steel that I am providing. Not the area of steel required here, but the area of steel that I am providing. So to do that, I, again, write this equation down. This is very, very handy for slabs. The area of steel that you are providing is equal to the area of steel of 1 bar times 12 inches divided by S, which in this case would be 0.31 for number 5 times 12 divided by our chosen spacing of 18 inches. And that gives you 0.207 inches squared. That's the steel that we are providing per foot. Now I can do my strength check. Remember that the slab, the one-way slab, is basically a wide, shallow, rectangular beam. So I can and will use my equation for a singly reinforced rectangular beam. Here I plug in my provided area steel times 60. There's my D, provided area steel, 60. The slab is 3 KSI and the assumed width is 12. That gives me 47.4 kip inches as my capacity, which is greater than my demand of 44.8. So we're good. Any questions on the positive side?
Yeah, Professor, quick question. Could you please go back to the last slide? For the area of steel, the 12 is the width, right?
Right here?
Yeah, it's this.
Actually, it's not. It is, but it isn't. What it is this area of steel is what you're providing per foot. And why do you want it per foot? Because we're designing it per foot. So the 12 is basically just 12 inches per foot. That's where that comes from.
Okay.
Oh,
So,
okay.
Professor,
Yeah.
does the nominal moment in this case is like 47.4 kip inch per foot?
It is.
Okay.
And our design moment was 44.8 kip inch. That too was per foot.
Okay. Yeah.
Technically, everything we're doing is per
It's per
foot
foot.
because we chose a 12-inch wide strip to design to.
Right. Okay. That makes sense.
Okay. All right, now we're going to move to the negative moment region. The negative moment region is where the tension is in the top of the slab instead of the bottom of the slab. So this occurs right at the supports. In the image that I had of our design, you had the positive moments in the middle between the beams. The maximum negative moment is at the beams. That's where you develop the tension in the top of the slab. So we're going to use number 5s again. Our D is the same D. And okay, so we're going to go through this again. Only this time my design moment is 62.7 kip inch. So that gives me 294 PSI. I look it up in the same table, but now rho is 0053 is greater than 0033. So I've met my minimum steel. It is less than 0136, so I'm okay for my maximum steel. And the area steel that I need is rho times B times D is 0.282 inches squared. So the required spacing of a number 5 rebar, again, here's this very handy equation. You take the area of a bar divided by the required area times 12, and that gives you 13.19 inches on center. Again, by design, this is my maximum spacing. The maximum spacing is the lesser of 5H, which is 27.5 or 18, same as before. But now the 13.19 is going to control. Oh, there's a typo. Just when you think you got them all, right? Let's see. I got to fix that one. Sorry, folks. That is typo 219. And let's go back to the current slide. There we are. Okay, so I'm mumbling to myself, but what controls is not the 18, it's the 13. So because my maximum is 13.19, I am just going to round down to the nearest increment of 2 inches for convenience. So I'm going to tell them to build this with number 5s at 12. Now, am I done? No, I still need to verify that phi min is greater than mu. So I'm going to calculate my provided area of steel, which is the area of the bar times my times 12 over my bar spacing, which is also 12. So the area of steel that I'm providing is 0.31 inches squared. And I plug that into my flexural equation. So there's my area of steel, 60 KSI, D, AS, FY, F prime C, B. And that gives me 69.2 kip inch, greater than 62.7 kip inch. So therefore, my chosen rebar arrangement is satisfactory. Number 5s at 12 inches on center. And then I do a design sketch. And this is my design sketch. For my maximum positive moment, I put the bars on the bottom. And we found that we needed number 5s at 18. So those go on the bottom. On the top, where I have negative moments, I need number 5s at 12. But as you can see, I don't need to extend those bars all the way across because in the middle here, I do not have a negative moment. It's all positive moment. So it's a little bit beyond the scope of this example to figure out how far out these bars need to go. That's readily, it's not that hard to figure that out. It's just beyond the scope of what we've learned so far. But the point is, for negative moment, the steel goes to the top. And for the bottom, for the positive moment, the steel goes on the bottom. And it is perfectly normal and customary to have different bar spacings at the top and at the bottom.
Professor,
Yes.
how do you know, or on the top, where they have the spacing, how do you know there's, would you say there was 0? I forgot what you say, why there's no rebar on that space.
Okay, let me draw you a quick little diagram.
Okay.
Hopefully this will help everybody. So this is just a flashback review from your statics of materials, right? So your moment is 0 at the end. Or I'm sorry, no, you have a negative moment at the end. So you have negative moment at the end. That moment grows to a positive moment and then becomes negative again at the other support. And then it carries on to the next bay. So you have negative moment at the supports here and here, and you have a positive moment in the middle. The negative moment magnitude was the 62.7, so that was here. And the positive moment was 42 or something like that. That was here. So I drew this gross and out of scale, but the point is there's an inflection point here and here, here and here. So to the left of the inflection point, you have negative moment. To the right of the inflection point, you have negative moment. Between the two inflection points, at least theoretically, you have no negative moment. It's all positive moment. So you don't need steel in the top. You only need a steel in the bottom.
Yeah, because positive only goes in the bottom.
Right.
Okay.
Okay.
Thank you.
It is a little more complicated. The code does have something to say about where the design is theoretically 0. You need to carry that steel out a little bit further. But again, it was kind of outside of the scope of this problem to calculate how far these bars need to go. But the principle is they don't need to go all the way across, because here you just have positive moments.
Professor, I have a question.
Sure.
You found spacing being 13.19,
Here.
and you ended
Yes.
up with a 12 on center. Why is
Yes.
it?
Mhm.
Why did that happen? Like, how did it switch to 12 inches?
Because you're not going to ask a contractor and a construction company to put number 5s at 13.19 inches on center. You're not going to do that, because you know that if you did that, somebody's going to come back to your office with a shovel and they're going to hit you over the head, because that's going to make them very angry. So since you're not going to tell them to put it at 13.19 inches on center, are you going to tell them to put them at 13 inches on center? Well, then maybe they'll only hit you with a smaller piece of rebar instead of a shovel, but they're still not going to be happy. The point is, you as a designer calculate what the maximum spacing is by design, and then you're going to choose something that they can build.
Why not 14 then?
I'm so happy you asked that question. Why not 14? And can somebody tell me why not 14?
It's exceeded the maximum.
It has exceeded the maximum, but what you will find is if you put them at 14, then the area of steel that you have provided is 0.31 times 12 divided by 14. You're providing 0.266 inches squared. If I put 0.266 inches squared here and here, then you will find that your FEMN will be less than your demand, and it doesn't work.
So it's under reinforced.
It's under
Oh.
reinforced in the sense that you didn't put enough reinforcement in it. Yes.
Okay, but it's not technically wrong if your epsilon T is between 0.4 and 0.5, right? Oh, no, never mind, because we used phi as
No, hold
0.9
on.
already.
Hold on. You're going in the wrong direction. A bigger spacing is less steel. So you're
Yeah.
not going to have a problem with epsilon sub T. You're going to have a problem right here in showing that you actually provided enough steel. You didn't put enough steel in there. The larger the spacing is, the smaller the area of steel you're providing.
Okay, that makes sense.
Okay. Any other questions on this lecture? I think
So
that was,
Professor, will 13
Oh.
be will 13 on center be wrong or just not practical?
13 inches on center would not be wrong, because you are providing more steel than the minimum. So you will have FEMN greater than MU. So it is not wrong, but you're still probably going to get some pushback from the contractor, who's going to say, what's this 13 inches on center? And maybe they will do it, and maybe they'll push back and say, that's, I don't want to put them at 13, just give me 12. Give me something to the nearest 2 inches. It's kind of an experience thing.
Got it.
So no, it's not wrong at all. It's just that maybe you've had the experience that, we do 13 inches all the time. Nobody ever complains about it. Or maybe you have the experience of, Well, they always push back on that. They always ask in an RFI, then I got to answer the RFI, then I got to change my drawings. Nah, we'll just put it at 12 and everybody's happy.
Got it. Thank you.
Okay.
Contractor hates odd number.
I would think so until you get down to a really small spacing. If you're in like the 3, the 4, the 5-inch range, then you put what you need. But if you're above like 6 inches, then I would say go to the nearest 2 inches. Okay, we got a little bit more to go in this. I forgot about this last little thing here. This is actually back to beam design. And it's a thing called skin reinforcement. And here's how it works. On deep beams, even if you have a lot of steel at the bottom here, you could develop some pretty unacceptably sized cracks going up the beam because all your steel's at the bottom. So the code requires that you put a minimum amount of steel on the sides of the beam to help staple it and keep it the cracks acceptable. So what the code says in section 9723, that if the beam depth, the whole depth here is 36 inches or greater than 36 inches, then you have to provide skin reinforcement. The code does not specify the size or the required area steel, so they don't say number 4s and number 5s, but they limit the spacing S per 2432, but they limit the spacing. Okay, I'm trying to follow my own stuff here. We're going to cover later what that spacing is because it's part of another lecture, but just be aware that the spacing is restricted by 2432. Skin reinforcement must be extended up or down from the tensile face. So here the tensile face is at the bottom, a distance of h/2 up. So you got to cover at least halfway in the beam with rebar on the skin, on the surface, at a spacing not to exceed S, dictated by 2432. And that is it.
Professor, I had a question on the last slide. So if we change H, would our S change? For example, if our height gets smaller, yeah, okay.
Yeah, Okay, good question.
Professor?
Yeah.
So I feel like the most confusing part of like this whole lecture is when you find the maximum moment, which exact equation you need to use. The W ln squared over 8 seems like the most simple to me because it's simply supported, but like all the other ones, I don't really understand what it's telling me. I don't know if there's like a table in the book that breaks down like an illustration.
No, there isn't. I actually did a better job than the textbook did. The textbook kind of just tells you, if I remember right. But what I did is I broke it down in this lecture. If you go back up, like I said, you can download this. So go to, let's see, where did I start outlining that? Here. So slide 29. And so what I've done is I've broken it down between positive moments and negative moments. Positive moments are where you design the rebar at the bottom of the slab. Negative moments are where you design the rebar at the top of the slab. And for each condition, I've pointed to where that location is. So if you have a simply supported slab, come on, it's not working. There we are. If you have a simply supported slab, which is not what I've drawn at all, a simply supported slab would just be a concrete on rollers, then your maximum positive moment is where I'm pointing. It's at the middle of the slab. If you have simply supported, there is no negative moments because it's simply supported. So that's why I don't draw them at the ends. So WL squared over 8 is something that you're familiar with for beam design when you're simply supported. This rarely gets used in one-way slabs. because of what you see in the diagram here. You rarely have a simply supported. Still trying to get this thing to work for me here. Oh, I know why, because I'm not sharing it. All right, let me do this. Slideshow from the current slide. There we go. All right. So now this is with a continuous slab. And that's the problem, this whole thing, is that this cast in place concrete slab is continuous over many spans. That's why the WL squared over 8 almost never applies. What always applies are all the other conditions. So what you have to look at is positive moment or negative moment. Those are the two big classes. It's either I'm talking about the positive moment or I'm talking about the negative moment. And then where am I talking about it? Okay, so if it's a discontinuous end integral with the support at the end span, so this is the end span because this is the edge of the building. See the break line right here? That means it continues on to the right by so many spans, but this is the edge of the building. If this is the edge of the building, this is the end span. And if it's an discontinuous end integral with support, see how the slab is integral with this beam here? That would be integral with the support. So then your maximum positive moment is going to be WL squared over 14. If the end is unrestrained, in other words, there's no beam here, the slab just stops. Then you would have WL squared over 11 at the middle where your positive moment is. And on interior spans are all the other spans until you get to the other edge of the building. And for all interior spans, your WL squared over 16, which would be in the middle of the next bay. Okay, see how this works?
Yeah, I see better. Thank you.
Okay. And then for negative moments, see, this is a whole different class. Now we're talking about negative moments. Negative moments always occur at the face of the beams, never in the middle here. So you just have to be very deliberate about where am I talking about. Interior face of exterior support is right here. That's the interior face of the exterior support. And then again, it asks you, are you built integrally with this supporting spandrel beam? Well, as it's drawn, yes, it is. So that would be WL squared over 24. If it's not, well, this was a little odd, but if it's built integrally with a supporting column, that means there's no beam here, basically. Then your WL squared over 16, same location. But now, different location. Exterior face of first interior support is right here. This is the exterior face of the first interior support. If I have two spans, it's WL squared over 9. If I have more than two spans, it's WL squared over 10. See, so you just have to look at positive moment, negative moment. Okay, now where am I talking about? Interior face, exterior face. Okay, once you have the location nailed down, then you look at, all right, how is it being built? Is it two spans or more than two spans? Is it integral with a supporting spandrel beam or not? And that's how you get to these proper equations.
Professor, what's a spandrel beam?
Spandrel beam is just a beam that's on the outside of a building. It could be the way that I drew it here, or it could extend up above the deck, or the slab can come over and turn upward sometimes so that you don't drive your car off the building. But that's basically what it means. It's just a beam on the perimeter of the building.
It's like a parapet?
It could be. Could
Okay.
be. Okay, and then Simon asked, when do we use shear VU? that's coming in a few lectures when we start talking about shear design. So I'll put a pin in that question until we get to that lecture.
Professor, for the skin reinforcement,
Yes,
that's only for beams, right? Not for slabs. I just wanna like,
absolutely. You
okay,
would,
because
yes,
you were talking about slabs and then at the last part, it's a beam.
that's right. It was just a tail on topic that I
Okay.
couldn't find a better place to put.
Okay.
All right. Now, what we need to do is tonight's lecture is actually pretty long. And it's not nearly as light and fluffy as the solid slab one. So without any further ado, let us do.
Professor, I don't think you uploaded lecture 6 on Blackboard.
I didn't. I thought I did. I think I put the homework there, but I didn't put, okay. Thank you. I will do that before I go home today. Let me write that down. Lecture 6 to Blackboard. Okay, will do. All right, tonight's lecture is about T-beams, analysis, and design. Now, I know fully well there is very slim chance that we're going to get all the way through this lecture in the next hour and 10 minutes. Like winning the lottery, slim. But we'll see how far we can get. If you look at my syllabus, there is, we have 2 days built into this schedule that are TBD, which are really just catch-up days. And so I'm not too concerned about it, but we can't get too far behind either. As I'm sure you guys are feeling, this is really an accelerated course. So we have 10 weeks to do 16 weeks of work. And that's kind of where we are. So let's see how far we can get on T-beams. What is a T-beam? This is the same diagram that I just used at the beginning of the last lecture to show you what a one-way slab is. So the one-way slab is designed to span from beam to beam. And that's fine. That's what the entire last lecture was all about. Now what we're talking about, and I want to make sure this is clear before we really dig into this. Now what we're talking about is the design of these beams. These beams now are spanning from end to end. They're being loaded up by the loads from the slab dumping into the beam, but we've changed direction. We are not spanning this way with the beam. The beams are spanning this way. Everybody see my cursor? They're spanning along the length of the beam. But this concrete is in fact here. So we can use the concrete that is really spanning this way, and we can turn it this way and use that concrete, at least some of it, for the design of the beam. So all of this concrete here does a wonderful job of being the compression member for this beam. That's why it's called a T-beam. We're using some of this concrete up here to help in the design of our beam. Supporting beams are usually poured with the one-way or two-way slabs. So this whole section is all poured together in one pour. So there's no separation between our one-way slab that we just talked about and our T-beam that we're starting to talk about. It's all the same concrete. So if I look at what I just showed you in isometric, if I look at it in section, here's that one-way slab. We just designed that one-way slab spanning from beam to beam, okay? We're done with that. That's done. We're not doing that anymore. Now what we're designing is this beam or this beam. So the slab between the beams also, in addition to being a beam of its own, it also acts as the compression flange, strengthening the beams running in and out of this page. The flanges are currently sized for one-way or two-way slab behavior, but the beams are either analyzed if all the variables are known or assumed, or the beams are designed. Beam design can use the tools to help hone in on a solution, or they may be purely iterative. Kind of depends on the complexity. Okay. To start off, though, we need to have a definition of an effective flange width. Stresses in the flange are not uniform, and they are difficult to design with. Okay, so here's an isometric of a T-beam. This is the web. This is the flange of my T-beam. Looking at an isometric view of the T-beam, this is an illustration of the stresses, the compressive stresses, when this beam is in flexure. The compressive stresses in that flange vary from nothing to a maximum back to nothing over some width. And the reason for that is called shear lag. So the actual stress profile due to shear lag, the normal stresses diminish as the distance from the center of the beam increases. So right over the center of the beam, you have your maximum strain, maximum stress in that concrete, but it doesn't stay constant. The further away from the web you go, the less stress you actually have in that concrete. Well, this is very difficult to design to. So we're going to replace it with this. You guys recognize this? This block sort of thing?
Yeah, it's what we did on the one-way slab.
Is what we did on the beams and the one-way slab.
Yeah.
This is the Whitney stress block. Only for the Whitney stress block, before we knew what the width was, we just needed to calculate what the depth was, little a. Here, we don't know what the width is because the width is not the whole width of concrete, it's some effective width, B sub F. The stress in the Whitney stress block is the same, 0.85 F prime C, just like we did for beams. So the actual stress profile can be replaced with an effective stress profile that represents the same compressive force. Simplified stress profile follows the Whitney stress block profile, rectangular in shape with a uniform stress of 0.85 F prime C, a width of B sub F, and known as the effective width. So what is the effective width? ACI Section 632 prescribes the geometry of T-beams and L-beams. This is a T-beam. If you only have flange on one side, we call that an L-beam. So some general terminology. When we're dealing with the T-beam, the width of the stem is B sub W. The width of the effective flange is B sub F, and it's known as the effective flange. But this distance of the overhang on the left or on the right is the overhanging flange width. For T-beams, table 6321 gives that the overhanging flange width is the least of 8 times the thickness of the slab, where the slab is H, so that the effective width for this condition would be 16 times H, because you get 8 times H here, 8 times H here, plus you get the width of the web. So the total is 16H plus BW. Or you can get SW over 2 as the overhanging flange width. S sub W is the space from beam to beam. So S sub W is from the inside face to inside face to the next beam. So you could have an S sub W1 on one side and S sub W2 on the other side, plus the web width, right? So that'd be S sub W1 over 2 plus S sub W2 over 2 plus B sub W. Or you have a limitation on the overhanging flange width based on the span of the beam. So L sub n is the span of the beam in and out of the page. And the overhanging flange cannot be more than L sub n over 8. So the effective width would be L sub n over 4. You get the left side, the right side, plus the width of the web. Whichever of these three is the least is the one that controls. Any questions there? Okay. For L beams, you don't get quite as much of an overhanging flange on an L beam. So it is the least of 6 times the height of the slab. So the effective width would be 6 times the thickness of the slab plus the width of the beam. Or you can get S sub W over 2 is the overhanging flange. In other words, your overhanging flange cannot extend more than halfway to the next beam because that beam is using this half of the flange. You can't double dip. So that's why this restriction of SW over 2. So the overhanging width would be SW over 2 plus the width of the beam, or LN over 12. See, they're more restrictive when you just have one overhanging flange on one side. So your effective width will be LN over 12 plus the width of the web. And again, whichever of these is the least is the one that controls. Okay, so for example, given the geometry below, find the effective width for the T-beam and for the L-beam. We can assume that the span of the beams is 27 feet. So the inside to inside is 12 feet. For this side, it's 14 feet. For the other side, the height of the slab is 5.5 inches. The width of the beam is 12 inches. So for the T-beams, we have 16H plus BW, or 16 times 5.5 plus 12 is 100 inches. Or half of the clear spacing on one side plus half of the clear spacing on the other side plus the beam width. So I have 12 times 12 inches per foot over 2 plus 14 times 12 inches per foot over 2 plus the beam width of 12, 168. Or L over 4 plus BW, as we said, the span is 27 feet. So 27 times 12 inches per foot over 4 plus 12 is 93. Of these three, 93 inches will control. So then we would design this beam assuming that the width of concrete up here is 93 inches. For L beams, we have 6H plus BW, or 6 times 5.5 plus 12 is 45 inches, or half of the clear spacing plus the beam width is 84 inches, or LN over 12 plus the beam width is 27 times 12 inches per foot over 12 plus 12, 39 inches. So in this case, 39 inches would control. And again, you can see for an L beam, my effective width is quite a bit less at 39 inches than the T beam at 93 inches. Any questions on example 1?
I have a quick question, Professor. What exactly we found out? Like, what is 93 inches?
The effective width of the flange.
I see. Thanks.
So do you divide that one, like, So it's 93 minus 12 and then divided by 2. So it'll be equal in both sides.
No, we don't do that. What we're trying to find, and back to Omer's question as well, is when we design this beam, we can't use all this concrete. We only use the concrete that is in the effective width.
Yeah.
So when we go to analyze or design this T-beam, the only concrete that exists for the purposes of our beam is what's in the red rectangles. Everything outside of the red rectangles does not exist for the design of that beam. So the
Yes.
width of this rectangle is 93 inches. And over here, the width of this rectangle is 39 inches. And everything outside of these red rectangles doesn't exist.
Are we always going to use the lowest measurement we find?
Yes, code requires it.
Professor, so the 93 inches also is on the top of the, like that makes up the T, the red rectangle you have on top of the T-beam?
Yes.
Okay.
The 93 inches is from here to here.
Is
And
that
it is,
placed? I'm sorry.
And
Is that placed exactly in the middle of that T-beam, or does the difference of span have anything, or does the difference of span change the position of it since it's 12 feet on one side, 14 on the other?
it could, that's a good point. It could, if one span was large and the other one was smaller, and this was the number that controlled, then it could be offset a little bit. But as you will see later in this lecture, that doesn't change anything for your design. But then that's a
Thank
great
you.
point, but in the end, it won't change your capacity.
Professor,
Yes?
so the 84 is the width of the beam, right? Or
This 84?
yeah.
No, that 84 doesn't apply.
Okay, so then the 39 would be the width of the both of the beams?
No, the 39 is the width of this effective flange.
That's only for L beam.
That's for the L beam.
Okay.
The width of the beam is given, that's 12.
Oh, yeah.
That never changes.
That's what I was trying to figure. Okay, yeah.
This is 12, this is 12, and that's part of the problem statement. That doesn't change.
Okay, yeah, that's given.
The only thing that you have to figure out is the effective
L.
effective width of the L and the T.
Okay, got it.
Okay?
Got it.
All right. I think this is probably a good time to take a little break. So why don't we take a 7? Let's get back at 7:10, okay? Still got a lot to cover. But let's reconvene here at 6:10, okay? All right, I am back. And let's see, pushing forward. Okay, so what happens if we have negative moments? What do we do then? So if you have a negative moment, then you're putting your stem in compression and your flange is in tension. So the effective flange width of a T-beam in negative moment is found the same way as for the positive moment. B sub F is determined from table 6321 in the same way. So everything we just did applies for negative moments as well. ACI 318 section 2434 states that the flexural steel in the flange of the T-beam must be distributed over a width of Ln over 10. So it's just based on the span over 10 is where you need to locate all of your steel. If you put steel too far out here, it's really not very effective in the strength of the T-beam. If the effective width B sub F is wider than L sub n over 10, then you have to add some reinforcement across the whole effective width to control your cracking. The minimum steel requirements of ACI 318-9612 are repeated here. Okay, so remember we've been doing this. For every beam problem, we got to check our minimum steel. And these two equations do not change. The only thing that changes is if you have a regular where the flange is in compression and the stem is in tension, then B sub W is the width of the stem. But if it is reversed and the flange is in tension, then B sub W is the lesser of the width of this flange or 2 times the width of the stem. It's a little obscure, but that's what you do if you have this condition with negative moments. Then you check your minimum steel with the lesser of your effective flange or 2 times the width of your stem. For the purposes of analysis, the general problem above can be simplified to that below. See, so this is the monolithic concrete pour. And what we're going to do is simplify this whole monolithic pour to just a simple T-beam. Like I said before, everything outside of the effective flange width doesn't exist. All this concrete vaporized, all this concrete gone. This is the only concrete that we're concerned about. This T-beam is fully dimensionally defined by the problem statement and the calculated effective width B sub F. Okay, now, this is in parentheses because this is really just for the purposes of the class. But if in this class, in a homework or exam, if I give you a T-beam and I tell you how wide the effective flange width is, if there's some dimension here, then you can assume that the effective width B sub F has already been calculated and given to you. Okay, this is really important. If I draw a T-beam like this and I say this is 60 inches, then go with it. Go with 60 inches. If, however, I draw a beam kind of more like this and I tell you how thick the flange is and I tell you how far it is to the next beam, then you have to figure out what the effective width is. Sometimes I do it this way. Sometimes I don't want you to spend all your time on that, so I'll do it this way and I'll tell you how wide to assume your width is. Okay, does that make sense?
If you, Professor, let's say, if you give us the width, can we use that one to find the thickness?
No. No.
Okay.
If
Because
I,
it's conditional, right?
yes, because you don't know which of the 3 cases I've assumed.
Yeah. Okay.
Say, so if I give this to you as 102, I'm going to tell you what the flange thickness is. I'm not going to make you reverse engineer what the flange thickness is.
Okay.
Okay. All right. Depending on a number of factors, including the flange thickness H, the steel ratio ρ, and the concrete strength F prime C, the compression block may be fully contained in the flange, like this. Okay, so you can see that little a is less than the thickness of the flange. This is the most common case. So the compression block is always as wide as your effective width, but it may be less deep than your flange, in which case the beam reacts like a rectangular beam. All the concrete below this little a, all the concrete below the red hatch is cracked concrete anyway. So the beam does not know that it's not a solid, ginormous beam as opposed to being this T-beam shape. It doesn't know any different. So if you have this case, then this is known as a rectangular T-beam case. Because again, the beam doesn't know that it's a T-beam. It's behaving just like a rectangular beam of this whole giant width. Or, and by the way, this is what you hope for. This is the simpler way to analyze or design the beams. But you could have the case where the compression block may extend down into the web of the beam. And that looks like this. So now it's not a rectangular beam anymore. The compression block is not a simple rectangle anymore. This is the more complicated case. This is what's known as true T-beam behavior. For a T-beam analysis or design, we first assume the rectangular beam behavior, because that's what we're hoping for, and then we check our assumption by testing whether or not A is greater than H. A is the depth of the Whitney stress block, H is the depth of the slab. If so, then we, or when I say if so, if A is greater than H, then we switch to a true beam behavior assumptions and we have to solve for little a, which I will give you some tools in your toolbox to do that with. Okay, so here's an example. Here I've got a T-beam. I told you what H is. I've told you what the overall depth is. I give you the width of the beam. I do not tell you what the effective width is. I tell you what the steel is, 3 number 10s. The concrete is 3,000 PSI. The rebar is 60 KSI. D is 21.5 inches. I give you that. The beam spacing, or the span of the beam, is 32 feet. And the beam spacing is 18 feet on center to either side. Okay, so that's the problem statement. Let's stop here for a moment. When you're doing these as homework, and particularly when you do these on an exam, it is best to always note, what do you know and what do you not know? What did I tell you and what did I not tell you? And in this particular problem, you know everything except the effective width. Okay, so once you decide what the effective width is, this becomes an analysis problem because everything is known. A design problem would be where the area of steel is not known, or the depth is not known, or any combination of those. But this is an analysis problem. So we want to analyze what is the flexural strength of this beam. Solution. First, we have to find our effective width. So we go through the same exercise, 16 times the height of the slab plus the stem width is 20 inches. So that's 116. I go halfway to the next beam over 2, or halfway to the next beam plus halfway to the next beam plus the width of the stem. That gives me 236 inches. Or I go span over 4 plus the width of the stem, 32 times 12 inches per foot over 4 plus 20, 116 inches. In this case, both of these controlled. So that's my effective width, 116 inches. Area steel is 3 number 10, so 3 times, and again, look this up in that table 8.2. 3 times 1.27 is 3.81 inches squared. So I can solve for little a. Little a is ASFY over 0.85 F prime CB. This never changes. So that's 3.81, 60, 3, 116. Why did I use 116 and not 20? Is everybody straight on that, or is that confusing?
Yeah, can you explain that, please?
So this is a beam in positive bending. The steel is on the bottom. So the bottom is in tension. The compression is on the top. So the compression is going to be here. That's the compression block. So if the Whitney stress block is as wide as the effective flange, then that's why this is 116, not 20. If it was negative bending and your compression was down here in the bottom, then this would be 20. Does that make sense?
In this case, are we gonna solve for the negative moment as well?
Nope, there's no negative moment in this case.
Okay.
If I had a negative moment, I would have to give you another diagram with steel up at the top. And that's not part of this problem.
Okay.
Okay. So little a is 0.77 inches. Now you make your comparison. 0.77 is most certainly less than 6 inches. So therefore, this T-beam is a rectangular beam for design and analysis purposes. And to draw it in there, then what we're saying is the Whitney stress block looks like that. This is 116 inches wide, and it is 0.77 inches deep. That is the whole stress block. Okay, therefore, because the beam is rectangular, we can use everything we've already learned for singly reinforced rectangular beams. So from here on out, it just becomes an analysis problem of a rectangular beam. We check our maximum steel ratio, which we do by finding epsilon sub t. So first I find C is A over beta 1. Beta 1 is 0.85. So C is 0.91 inches. Epsilon sub t is 0.003. D minus C over C is 0.0679, much greater than 0.005, so no problem. Phi is equal to 0.9. My minimum steel requirement is based on B sub, let's see, that's B sub W. So B sub W is the width of the stem. Why is it the width of the stem? Remember, the minimum steel requirement was to be sure that if this beam were to crack, you have enough steel to have additional strength beyond the load it took to crack it. If this beam is in positive bending, where's it going to crack? It's going to crack at the bottom. With positive bending, it'll crack at the bottom. So the width of the stem that we put in here is the width of the concrete at the bottom. That's what we're trying to protect against. So the width of the stem is 20. Okay, so you've used this a few times now. Minimum steel is 1.18, or minimum steel is 1.44. 1.44 will control. We are providing 3.81 is greater than 1.44, so we're okay there. So here I checked my maximum steel. Here I've checked my minimum steel. Now I just need to calculate my capacity. This is being treated as a rectangular beam, so I can use my flexural equation. So I plug in my area steel, my yield, D, AS, FY, F prime C, B effective, and I get 4344 kip inch or 362 kip feet. And that's the answer to this problem. Any questions on this example?
So only for minimum, we use the BW.
Yes. Anything that has to do with the compression block is 116. That's the width of my compression block. But the minimum steel is to protect against cracking. So it would crack across the bottom. So that's BW.
But is it gonna flip, Professor, if we have a given negative moment?
If you have a negative moment, that's where you have to flip it. Now your tension's on the top. And that's where we just went over that BW is actually B sub F or 2 times the width of the stem, whichever is least.
Okay.
Okay.
In this problem, why don't we compare phi mn to mu? I'm not even sure if you gave us an mu in the beginning.
Just answered your own question. I did not give you an mu in the beginning. This is an analysis problem where I just want to know what is the strength of the beam. It's not a design problem where I give you a load and you design the steel to resist that load. It's just an analysis problem where everything is given, so you just tell me what the strength is.
Okay, I see. Thank you.
Sure. All right, next example. This is similar, but now the flange is only 3 inches thick instead of 6 inches thick. And we have a lot more steel now. Instead of 3 number 10s, we have 6 number 11s. So we're going to do it again. Same 3,000, 60, 21 and a half, everything else is the same. Analyze the flexural strength of the beam. So again, the question is asking for the flexural strength of the beam. So it's not a design. I don't give you a load in this particular one. We're just looking for what is the theoretical strength. Solution. Again, we have to find the effective width, but this time it's different. We can't just use the same numbers because H is only 3 now instead of 6. So it is either 68 or it is 236 or it is 116. This time the 68 will control. So my effective width this time is only 68 inches. My area of steel is 6 times 1.56 inches squared. That's 9.36 inches squared. So little a, ASFY over 0.85 F prime CB gives me 3.24 inches. What is significant about 3.24 inches?
It's bigger than your thickness.
It is bigger than my thickness. Okay. This is where most students have the confusion. So I want to cover this slowly and clearly, that this is really where a lot of people get tripped up. This A does not exist. It is not real because it's greater than the thickness of the flange, but it was based on the full width of the flange right there, 68. So this is assuming concrete that doesn't exist. So you cannot use this number ever again. That number is only there to tell you that the rectangular assumption for this beam is invalid. And that's it. So A is greater than H, equal to 3 inches. Therefore, this T-beam is a true T-beam, and the A that we just found, this 3.24, is incorrect. We dump this value. Do not use this value anywhere else in your problem because it's based on fictitious facts that we have proven do not exist. Okay? We have to basically start over. So starting over, what we recognize is that the entire overhanging flange is going to be activated. And A is going to be something greater than the width or the depth of that flange, something greater. So this is what my compression block is going to end up looking like. It's going to look like the entire area of the overhanging flange and some area of the web that's deeper than the flange. So now we know the entire flange is in compression. So we can take that force, C sub F is the compression in the flange. We can take that out of the summation of forces. So what we're going to do is we're going to break the total compressive force into two components. The middle component is C sub W, the compression in the web, and the hatched component is C sub F, the compression in the flange. The compression in the flange can be solved right now. We can solve it. It's going to be 0.85 F prime C is the stress. The height of the block is H, and the width of the block is the overall width minus the web. So that's 0.85 times 3,000 PSI times the thickness of 3 times a width of 68 minus 20. That gives me 367.2 kips. So I know that. Once I proved that A is deeper than the flange, then I can take the whole force in the flange and take it out of the equation. So T equals to ASFY is 9.36 times 60 is 561.6 kips. Therefore, see this equation right here, my equality? I know what T is. I know what C sub F is. I can solve for C sub W. C sub W is going to be T minus the compression in the flange. So 561.6 minus 367.2 leaves me with 194.4 kips. So I know this block in the middle here has to be good for 194.4 kips. If it isn't, we don't have equilibrium. So it has to be. Now what I can say is that little a is equal to the compressive force in the web divided by 0.85 F prime C times the width of the web. So I'm basically just doing like a rectangular beam analysis for the web portion. So I can say that little a is 194.4 over 0.85 F prime C times the width of the web, 20 inches, and that gives me 3.81 inches. Little a is 3.81 inches. Okay, let's back up here for a second. Now you can see that 3.24 is the wrong answer. It's just flat out wrong. And we never intended for that to be our answer. It was only there to tell us that we need to do true T-beam behavior. Now that we know that it's true T-beam behavior, we do this analysis and we get 3.81 inches. That is the right answer. Does that make sense?
I have a question. The very first statement, it says we can take the force C sub F out of the summation of forces.
Yes.
So why do we still calculate it?
We need to know what it is so we can take it away from the total. See, the total horizontal force is equal to ASFY, which is
C sub F is the tension inside the flange, right?
C sub F is the compression.
Compression.
in the overhanging flange.
Oh, compression.
The total tension is ASFY. That's 561.6 kips. When I say you can take that out of the summation of forces, we calculate what it is, 367, and we take it away from the total 561 so that we know what's in the web has to be the 194.4.
Oh, so when you said take it out, you meant like subtract it from the total, not like literally take it out of the equation.
Yes. Okay.
Thank you.
We're trying to isolate what we don't know is little a. And what we don't know is the compression force in the web of the girder. So we're taking what we do know out to find what's left. And that gets us to 3.81 inches. Since A, 3.81, is greater than H, 3 inches, we've confirmed that it is a true T-beam behavior. That's just a confirmation of what we found. Okay, now that we have little a, now we can get on with our lives. Check the maximum steel. C is equal to A over beta 1. Beta 1 is still 0.85. So again, this is the only true A. The A we found before is wrong. So like I said, just throw that away and only use this A that you found, assuming the true T-beam. 3.81 over 0.85, 4.48 inches. Epsilon sub T, I plug in my 21.5, 4.48, I get a typo. I thought I fixed that. It's actually 0114, not 00114. And there, that's where I fixed that. I just didn't go back far enough. Okay, so epsilon sub T is 0.114 greater than 0.005. So therefore, my phi is 0.9. My minimum steel, this is what we just did before. So it's 1.18 or it's 1.44. That one controls. My 9.36 inches squared is most certainly greater than 1.44. So we're okay there. Last step, we have to calculate our capacity. Here's the deal. For true T-beam behavior, we cannot use this equation. Okay, everybody get that? This is a no-no. Cannot use that. Why? Why can I not use my favorite equation?
Because we don't have F sub n.
The reason, that's close, but the reason is, see this B right here? That B right there is assuming that, or actually, let me say it this way. ASFY over 1.7 F prime CB is really representing A over 2. This is D minus A over 2. But this number here doesn't give me A over 2. And it doesn't work like that because the B is not consistent. If you had a rectangular stress block, then this is B and this is A and everything's consistent. But now we have this. So where's the centroid of that T shape? We don't know, but it's not at A over 2. So that's the real problem. The centroid of the compression is not located at A over 2. So we can't use this equation. Okay, I want to make sure everybody's crystal clear. If you have true T-beam behavior, do not use this equation. You'll get the wrong answer every time. So what do you do? This equation is only valid for singly reinforced rectangular beams. We don't have a rectangular beam, we have a T-beam. So in this case, we have to sum our forces to calculate the resisting moment. So here's a side view of the same beam. At the bottom of the beam, I have a tensile force. Halfway through the flange, I have C sub F, and at a distance of A over 2, I have C sub W. See how it's not as simple as it was before. T is at D from the top, C sub F is at H over 2 from the top, and C sub W is at A over 2 from the top. So really the only way to find our capacity is to sum our moments. And I find the easiest place to sum our moments about is the top of the beam, where that red dot is. Okay? Everybody remember summing your moments from statics and mechanics of materials? So we sum our moments equal to 0. And what we're going to say is if I go clockwise is positive, then T times D is one component. C sub F times H over 2 is going counterclockwise, so that's negative. And C sub W times A over 2 is also counterclockwise, so that's negative. And then the resisting moment that we're solving for is negative. So I flip, yes?
For the counterclockwise and clockwise, is that what those arrows mean right there? Or those are just the dimensions?
Those are just dimensions.
So then how do you know if it's going clockwise or counterclockwise?
See the arrow head here?
Yeah.
Tension is pulling, compression is pushing.
Okay.
Okay?
Yeah.
All right, so what I did here then is I just flipped Mn to the other side. So Mn is equal to T times D minus Cf times H over 2 minus Cw A over 2. And then I just plug in my numbers. I got my tension, it was on the other slide, but my tension was 561.6, D is given. My compression in the flange we found on the other slide, H over 2 is 3 over 2. And then we solve for C sub W and then A over 2. Run this all out, and what you get is 11,153 kip inches, or 929.4 kip feet. But remember, this is the nominal capacity. My allowable capacity is phi times Mn, or 0.9 times 929.4, for a final answer of 836 kip feet. Any other questions on this problem?
Professor, why did you do H over 2 and A over 2?
Because that's where the centroids of those flanges are. Let's go back to here. So the hatched area, vertically, where's the center of the hatched area?
Yeah, let me know.
It's at H over 2. H is 3 inches. So the centroid of the hatched area is at 1.5 inches down, or H over 2. Where is the centroid of this middle part?
A over 2, yeah.
A over 2. So that's why I got the wrong.
And why we don't do it for T as well?
T is given. T is at D from the top.
Oh, okay. Thank you.
Okay.
Can we use the axis theorem for this one to find the centroid for both of the flange and the real beam in the middle?
Yes, but it's more work. Okay, so the question was, can we, or let me rephrase the question if I may. The question was, can we find the center of gravity of this whole geometric shape and then use the whole compression, CW plus CF, at the center of gravity of the whole shape? Yes, you can. But in order to do so, you have to find where that center of gravity is. So you would have to take the area of the overhanging flange times a distance of h/2 plus the area of the web times a centroid of a/2, and then divide that by the area of the flange and the web together. And that basically gets you a resultant of C sub F and C sub W. Yes, that does work. But since in order to get the centroid, you have to use h/2 and a/2 to get there, it's actually more work than just keeping them separate and summing the two parts. All you're basically doing, if you did that, is combining CF and CW into one C at some other moment arm. But you still have to do this. You can't use this anyway. This is out. This is off the table. So all you're doing is using more math to consolidate these two vectors into one vector.
Okay, I thought after you find the centroid, you can use that formula, but it's not. Okay.
Yeah,
Because you
could,
said it's gonna be A over B technically,
yes.
right?
No, actually, you're right. You could. If you found where that centroid was, you would plug that in right here, and then you would sum your moments about the centroid of all of the compression. And yes, that would give you the same answer.
Okay.
Yes.
So it is like usable. Yeah,
Yes.
because for this one, I kind of lost for the sum of the moments.
Well, okay, hold on. Back up the trolley. This is not usable. What you'd have to use is AS FY D minus, and then that moment arm that you find. That's what you would use. You still can't use this. You'd have to use this. And to get that arm is a lot more work than doing this.
The moment arm is technically the distance from the top to the centroid, right?
That's right.
Okay.
That's right. But there's also something in that what you just said I want to be clear about. So yes, I could use this equation if I went to the work to find what that arm is, but I still cannot use this equation. So this equation is off the table, like I said, but the foundation of this equation is this equation, and if you did the work, yeah, you could find arm. However, I still don't recommend it because this formulation where we sum the moments from the top of the beam, that's going to be common practice for T-beams. It's also going to be common practice for doubly reinforced or compression steel beams. So you really should get comfortable doing this. This happens a lot.
Okay. Okay, that makes sense.
Okay. All right, where were we? We were, oh, design. Okay, so what we just did was the easy part. That was analysis. Now we move into design, and design's where the fun starts. So for design, we insert always. We always assume the T-beam will behave as a rectangular beam. We progress through the design until we get to a point where we can prove that either it is a rectangular beam, in which case we just complete it like we did before, or we determine that the beam will actually be a true T-beam, in which case we scrap everything and start over. Okay, that is the process. The process is assume it's rectangular until you prove that it isn't, and then start over or continue if it is. If the beam will act like a true T-beam, then the procedure is to proportion some of the total required steel to balance the fully activated flange and find that moment due to that steel, take that moment from the total moment, and then the portion of the moment left has to be designed from the web of the beam and is designed as a singly reinforced rectangular beam. So in other words, if you find that you actually have or trying to design something that wants to be a true T-beam, then what you're going to do is you're going to find the compression in the flange. You're going to balance that compression with some of the steel, find that resisting moment, take it away from the total design moment, and the moment that is left, all you're left with is a rectangular beam. So then you design the web like a rectangular beam, and then you add it all back together. And yes, I have one or two examples that will do just that. So if the flange is fully activated, then the compressive force in the flange, like we did before, C sub F is 0.85 F prime C, the height of the flange, and then the full effective width minus the web width. And that force is located at H/2 from the top of the beam. The portion of the total steel required to balance the flange is defined as the C sub F is the compression in the flange. So T sub F is the portion of the total that balances it. And that's equal to the same thing, 0.85 F prime C H BF minus BW is equal to AS. The little f stands for the portion of the total steel balancing the flange times Fy. The nominal moment capacity of this steel that perfectly balances the flange is VASF Fy d minus H/2, because the centroid of that compression is at H/2. The portion of the total design moment, mu, resisted by the web is then equal to the total design moment minus the resisting moment of the flange, where MUW is the new design load to design just the web as a singly reinforced rectangular beam. The steel found from this last step, ASW, is added to ASF to find the total required steel, AS required. Why is this so complicated? Well, because it's a T-beam. It could be rectangular or it could be true T, and you don't know because whether it acts like a true T-beam or it acts like a rectangular beam is entirely dependent on how much steel you provide. You don't know how much steel you're going to provide until you figure out how much steel you need. So this is the procedure. Once AS required is determined, then you pick a reinforcing scheme, number and size of bars. Then you perform your 3 checks, maximum steel, minimum steel, and your final capacity check. Okay, so let's do an example. This beam, and see how I dimensioned the effective flange here as 50 inches? So that means don't bother. Do not go through the effective flange width calculation. I've already done it for you. You can go on to the next step. The flange thickness is 3. The D distance, notice this is not to the bottom of the beam, but to the centroid of the steel, is given at 36 inches. Width of the web is 14, but I do not know the area of steel. This is 4,000 PSI concrete, 60 grade steel, D is 36 inches deep, width of the flange is 50 inches. Design this to resist 1,000 kip feet. Okay, so this is your classic design problem. I don't know the area of steel, but I know how much load I want to carry. Solution. Well, as always, we assume the solution will be a rectangular beam. So I attack it as if, let me draw draw a square here, I attack it as if this is the geometry of my beam until I know better. So mu over bd squared is 1,000 kip feet times 12 inch per foot over phi. B is my 50 inches. My D is 36 inches. That gives me 206 PSI. From my table, I have 0036 is required. So AS required is rho BD. 0036 times 50 times 36 is 6.48 inches squared. So far, everything is tracking exactly as if it was a rectangular beam. And for this beam, I will choose 9 number 8s in 2 rows, 5 in the lower, 4 in the upper. Check my minimum width. Per table A5, minimum width for 5 number 8s is 13.25 inches, less than my 14. We're cool there. My area of steel provided is 9 times the area of a number 8. So 9 times 0.79 is 7.11 inches squared. Is it rectangular? Well, if it is, then A is equal to ASFY over 0.85 F prime CB, which is 2.51 inches. 2.51 inches is less than my available 3 inches. So therefore, it is rectangular. Yay! That means it's a whole lot easier. So I need to do my minimum steel requirement, which is the 3 square root Fy over BWD, or 200 Fy over Fy BWD. So BW is equal to the stem width, which is 14 inches. So the first requirement yields me 1.6 inches. The second requirement yields me 1.68 inches, which is going to control. And I'm providing 7.11 inches squared, greater than 1.6 inch squared. Okay, check my maximum steel. A, as we found, is 2.51 inches. You don't really need to do this again. You can just pull it down from above because it was found to be rectangular. If it was found to be a T-beam, you got to do all over again, but it was rectangular, so I could have just used the 251 that I found above. C then is equal to 2.95. Epsilon T then is equal to 0.3361, much greater than 0.005, so phi is 0.9. Last step, because the rectangular assumption was valid, we can use this equation. So I plug in ASFY, D, ASFY, F prime C, B, F. I get 13,340 kip inch, or 1,112 kip feet. And that's my final capacity. And my demand was 1,000, so 1112 is greater than 1,000. Therefore, my design is acceptable. Please remember, how could you forget? I say it every time, but I need to see this or the problem is incomplete. This is what we're looking for. Okay, any questions on example number 4?
No questions, Professor.
Okay. Let's see. So I think we'll pick it up next time because I can't do example number 5 in 5 or 10 minutes. So let's pick it up next time.
I have a question, Professor.
Okay.
Can you go back one slide?
There we go. Yeah.
So we're only concerning for A if it's greater than or less than the thickness, right? And then the C does not, like, we don't care about it if is there any chance that the C will be greater than the thickness?
Absolutely. Many times it is. Many times A is just thinner than the flange, but little c is greater than the flange. But that's okay. That,
Because this is just the ratio of, right?
well, that's okay because c is the distance to the neutral axis. And
Okay.
A is the assumed thickness of the Whitney stress block. And yes, there is a little bit of an incongruency there between what we're assuming and reality. There is a little bit of an incongruency there. You remember the very first lecture where I did the integrals with the functions? That
Yeah.
would be the way to really nail it down, but you get a very small difference between that and this. So in the way that we are formulating this, the way that we are assuming this, many times C will be greater than the thickness of the flange, where A is not. And that's okay, because it falls within the parameters of the assumptions.
Okay. Makes
Okay,
sense.
good question. That was a very good question. Anybody else? Any other questions? Okay, during the break, I went ahead and posted this lecture onto Blackboard, so it's available right now for you to download. We are, let's see, where are we? We're on slide 276. So believe it or not, we're just a bit more than halfway on this. So we will pick it up on Thursday. Everybody have a great evening. I'll see you on Thursday.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you. Have a good one.
You too.